Hello, in this subsection we want to talk about derivatives. The idea here is introduce you to the concept of a derivative, talk about differentiation rules, and describe a little bit what its main uses are. In economics we use derivatives and calculus in general a lot. For example, if you want to characterize the shape of a function, the first and second derivatives become very handy to talk about whether the functions are increasing, decreasing, concave, convex. They are also used when you're trying to solve a maximization problem through first and second order conditions, and they are generally used when you are trying to describe phenomena like marginal changes. So whenever you face an economic problem and you are being asked about a marginal increase or a marginal change, you have to think in your head that mathematically what you are being asked for is to compute a derivative. Okay, for example, in economics, in your intermediate micro and macro classes, you often talk about the marginal utility, which is a change in utility when you increase consumption. You talked about marginal costs, marginal benefits. Economics is all about decisions in the margin, marginal cost versus marginal benefits. So at the end of the day, it's all about derivatives in mathematical terms. So it's very useful to review some of the basics of differentiation. And this is what we want to do here. So let me give you an application. For example, you may be asked about how would you calculate the change in cost when production is marginally increased. Now, another concept that is typically related to derivative is the idea of the slope. So when you have a linear function, remember, we define the slope of the linear function as the increase in the dependent variable, in this case, cost of production, when you change the independent variable, which would be the quantity produced. So if you increase production by 1 unit, by how much would you be increasing the cost? So in a linear function, basically the way to answer this question is to compute the slope. And we know how to do that even without calculus, just doing raise over run. Now, what if your function was quadratic? Could you do the same thing? Or how would you approach those type of problems? So let's think about a specific example to try to understand why do we need differentiation, particularly in economic problems. So there are, let me prepare the pencil here so we can do the computation. So let's consider a specific example. Let's say we are focusing on the red line, and the red line is representing your cost function, and we know that this red line passes through 3 points, 1, 2, 2, 4, and 3, 6. And you're being asked about, the marginal increase in cost when you change production. So we saw how to compute this. Basically, all you need is 2 out of these 3 points to compute the slope. For example, we can do the change in y, 6 minus 4, when you change x, 3 minus 2. And this is basically going to be 2. You can also do 4 minus 2 over 2 minus 1. This is also equal to 2. Or you can do 6 minus 2 over 3 minus 1, which again is going to be 2. So when you are thinking about a straight line, the slope is always going to be a constant. So it doesn't matter where you compute it or which points are you using or how far away these points are from each other, as long as you do the change in y over the change in x, you are going to get the same value for the slope. So it's, pretty straightforward. In other words, the steepness is the same. So when you have a linear cost function, the marginal increase in production is going to be independent of the actual level at which you are producing at the moment. Now let's think about what happens with a quadratic function, and this is kind of going to introduce us slowly to the idea of differentiation. So let's say we have the following blue line, which is a quadratic function that passes through 2 points, minus 2, 2, and this point x, and the equation of our quadratic function is minus x squared plus 6. Now let's say we want to do the same thing. We want to say, okay, let's join these 2 points through a line. Remember, the line that joins 2 points in a graph is called the secant. And let's compute the slope of that line. Now, the black straight line has a well-defined slope, which we know how to compute is a change in x when you change in y. So basically, this is y1 or y2 minus this value here is y1, which is equal to 2, over x2 minus x1, which is minus 2. So we can have the formula for the slope of this function, and the question is, could we use the slope of the secant to approximate the change in your costs when you increase production by 1 unit? Now, let's say we want to think about computing the slope of this quadratic function at 2 different points of approximation. So we can call the first one we computed in the previous slide as the one that goes through minus 2, 2 and x1, y1. So we computed the secant of that line. Now let's think about what happens if instead of doing it there, we do it at minus 2, 2 and x2, y2. Now, as you can see, these two secant lines have a different degree of steepness, so they are going to have a different slope. The first line is steeper than the second line, so the function of the secant is going to be different. Now, what is this indicating to us? That the steepness of a quadratic function is going to depend on the point at which you calculate it. So it's not the same as what we did in the previous slide, where we were thinking about a linear function, that no matter where we computed it and how far away were the 2 points at which we computed the slope, we always got the same number. So when we are thinking about a quadratic function, we will have to specify the slope at a specific point in the graph, because the slope is not going to be a constant anymore. Now, what is the best approximation for the slope of a quadratic function at a particular point? Well, it's not the secant line, it's the tangent line. The tangent line is the line that touches the graph at one and only one point. So it's basically this red line here. And that's going to be the slope of this quadratic function at minus 2, 2. Now, of course, if you want to compute the slope at a different point, you have to compute the slope of a different tangent, the tangent that touches the graph at that different point. Now, in general, for any function that is not a straight line, we are going to define the slope of a curve at a particular point as the slope of the tangent that passes through that point. So what is the slope telling us again? The slope is telling us the steepness of a function at a specific point, and it's giving you an indication of the rate of change of the function at that point. And if you think of it in those terms, it's pretty clear that when you have a quadratic function, the rate of change is going to be different depending at which point you are evaluating it. Now, how can we actually compute this? Well, remember, we said we could use the secant. So, for example, if we think about this blue line, the formula for the secant is something that we computed a few slides ago. Now, we cannot use this formula exactly at x equal to minus 2, because then we would have something that is divided by 0, and that's an operation that we cannot do. But what can we do instead? Well, what we can do is we can compute the formula of the secant for any two arbitrary numbers, and then start making the difference between the x's at which we compute it smaller and smaller. In other words, we are going to compute it for an arbitrary point and a point that is epsilon away from the initial point, and we are going to make that epsilon go to 0. So in this specific example here, I'm showing it to you with numbers, then we are going to look at it with equations. We can do this approximation either from the left or from the right. So let's say that we are moving from left to right. So as we move x from minus 2.5 all the way to minus 2, which is the point that we are interested in, and we plug that into this formula, we can find that the slope is changing. So at minus 2.5, the slope, which is the slope of the secant, actually not of the tangent, is 4.5. At point minus 2.3, the slope is 4.3. at minus 2.1 is 4.1. So as we are decreasing the difference between the two x points, we are seeing that the slope is approximating the number 4. If instead we go from right to left, so we move from here to here, and let's say we start from minus 1.5 all the way to minus 2, again, we see that at minus 1.5, using this formula, the slope is going to be 3.5, and minus 1.7 is 3.7, and minus 1.9 is 3.9, so on and so forth. The closer we get to minus 2, the closer this slope is becoming to 4. So a good guess of what the slope of this quadratic function is at point minus 2, 2 is a number 4. Now, the formula for the slope, which we are going to see a little bit later how to actually obtain, is a function itself. So the formula for the slope of the curve y, which is f of x at any point x, is going to be called the derivative. And it's denoted, it has different ways in which we can denote it, but typically is denoted by f prime of x, sometimes is denoted as dx over dy over dx. In other words, what's the change in y when we change x? So notice that this symbol here is the symbol of a partial change or a small change. When we were talking about the straight line, we were using this symbol. Typically, when we use delta, we are talking about slightly bigger changes. When we use this symbol here, we are talking about very small changes. So these are different ways in which we are going to, denote the derivative of a function at a particular point. And again, the derivative of a function is a function itself, and it's going to change depending on where you compute it. If you compute it for this red function at point t, the slope is going to be something that looks like this. If we do it at a different point, it's going to take on a different value. Now, the process of computing the derivative of a function is called differentiation. Why? Because again, you are doing the same thing as we did with the slope. With a straight line, it was what is the change in y when you change x. Here we are trying to do it, but for very, very small changes, because, as we said before, for most functions, the derivative is not going to be a constant. So to get the best possible approximation for the derivative, we want to make very small changes from the point at which we are trying to compute the derivative. Mathematically, how can we do this? We can do this by taking limits. So let's say we have a point x0 at which you want to compute the derivative, f prime at x0. So what can we do? Well, we add a very small number, h, and we look at the change. Again, this is just the change in y, f of x0 plus h, x0 plus a small number, minus f of x0, so this is a change in x, over the change in, this is a change in y over the change in x, which is x0 plus h minus x0, which is equal to h. And then what we do is we try to make that h value smaller and smaller and smaller. And that's how we are going to approximate the slope of the tangent line, and that's how we are going to get the derivative at point x0. Now, if that limit exists, it's not always going to exist, but if it does exist, we are going to say that the function f is differentiable at point x0. Now, if the limit exists for every point in the domain of our original function, then we are going to say that the function f is differentiable. And we are going to write the derivative more generally as f prime of x, or df over dx, or dy over dx. And that's going to be the mapping of x to the derivative. Now, if the limit does not exist at x0, we are going to say that the derivative of f at x0 is not well defined, or sometimes we are going to say that f is not differentiable at x0. So there are functions that are differentiable everywhere, and moreover, whose derivative is a continuous function, we are going to call those functions continuously differentiable. So a continuously differentiable function, or C1, is going to be a function with two properties. First, it's going to be differentiable. Second, the derivative is going to be a continuous function itself. It's not going to have jumps. Now, there are some functions that are differentiable at some points, but not all, and those are not going to be continuously differentiable. Now, using the formula I showed you before, we can compute the formula for the derivative for some of the commonly used functions that I was talking about in the previous subsection. And these are more compactly called differentiation rules. So you do not have to, actually do this small marginal change, take the limit, find the formula, because for many of the functions that we are going to use in the first and second years of your graduate program at Stony Brook, you're actually going to use one of the functions that I'm going to show you in a minute. So these rules or recipes are going to come very handy, and it's good that you get used to it. In the homework, you have a bunch of exercises that you can use to practice. Simon and Bloom also has a ton of examples. You can find some other examples online. So first, differentiation rule. The derivative of a constant is 0 at every point. So for example, if we have the function y equals to 5, what is the change in y when you change x? Well, it's 0, because y never changes. Y is always 5. So the formula for the derivative is equal to 0. Now, the derivative of a linear function is a constant, and it's basically the slope. We've seen this before. So if our function is a linear function a times x, the derivative is just going to be the value of the slope, which we've been using with the notation of a. So in this particular example, the derivative of this straight line is just going to be the number 5. Okay, so these are two that are straightforward. Now, the derivative of a quadratic function is going to be a linear function. So let's say that c is a number that we know, 3, 4, 5, 7. And our function is c times x squared, then the derivative is going to be 2 times c times x. So in this particular example that we have here, fx is equal to minus x squared. C is basically minus 1 in this example. So what is the derivative? It's minus 2 times x. So again, notice that the derivative is a function itself. Now, the derivative of a linear and quadratic function, and even for a constant functions, they are all subcases of this other rule, which is called the power rule. So if you have any function in which you have x to the power of n, where n is just a number, so this is some polynomial function, the derivative is always going to be n times x to the n minus 1. So let's look at it at an example. If f of x is x to the 4th, then its derivative is going to be 4. Remember the number n. This is a polynomial of degree of order 4 or degree 4. Is going to be n, which is 4, times x to the n minus 1, which is 3. Okay? If notice that a linear function is a function that has n equal to 1, and that's why f prime is 1 times x to the n minus 1. Any number to the 0 is 1. So this is just the number n. Okay, and okay, let's keep going. Now, remember that in the previous subsection, I was talking about the fact that you can do operations with functions. You can add them, subtract them, take the ratio, etc. Well, we have also some formulas for what is the derivative of a function, which is, the sum or the difference between two other functions. So when you have a function f, which is the sum of two functions, h of x and g of x, the derivative of the sum is simply the sum of the derivatives. Now, this rule actually allows us to calculate the derivative of a lot of cases that we typically use, for example, for a straight line. So previously, I talked about the slope of a straight line with an intercept of 0. Now we can think about the slope of a straight line with some positive intercept. So let's think about a straight line of the form ax plus b, as we've seen before. So this is the sum of two functions, the function h of x, which is a times x, and the function g of x, which is simply g. The derivative of h of x, using one of the previous rules, is simply a. The derivative of g of x, this is just a constant, is independent of x, is 0. So then the slope of a straight line that has a positive intercept is going to be equal to a. So let's look at this example. If f of x is 4x plus 2, our h function is 4x, its derivative is just 4. Our y function is 2, its derivative is 0. So the slope of this function is simply 4. Now we can also do the slope of a general quadratic function. So let's say our function is cx squared plus d, then our function h is cx squared, so its derivative is going to be 2 times c times x. We've seen this in the previous slide. Our function g of x is d, this is a constant, so its derivative is going to be 0. So the derivative of cx squared plus d is just going to be 2 times c times x. So let's look at this example. In this example, this is our h of x, so the derivative of h of x is going to be minus 2x. This is our g of x, so its derivative is just going to be 0. So the derivative of this particular function is simply minus 2x. Okay? Now there are more general rules. If you have a function that is some number, this is a number, which can be positive, negative, any real number, multiplied times another function, then the derivative is just the number times the derivative of the function g. Okay? So for example, in this case, f of x is 3 times x squared, so k here is equal to 3, g of x is equal to x squared, so the derivative of x is just going to be 3 times the derivative of gx, which is 2 times x, so 3 times 2 times x, so it's going to be equal to 6 times x. We also have another rule, which is when we have a function which is another function g of x to the power of n, we can basically use the following rule. So we think of this as kind of being a variable, so it's n times g of x to the n minus 1 times the derivative of g of x. So here it's an example. So here our g of x is equal to 3 minus 7 times x. So our f function is g of x to the minus 3. So what is f prime of x? F prime of x is going to be minus 3 times g of x to the minus 3 minus 1, which is minus 4, times the derivative of g when you change x, which is minus 7. Minus 7. Okay? So it's going to be minus 3 times g of x, which is 3 minus 7x to the minus 4, times minus 7. So this times 7. Or 21 times 3 minus 7x to the minus 4. Okay? Now, so let's think a little bit about an application. As I said before, the term marginal typically refers to differentiation or to a derivative. So let's think about a specific example. Let's say that our cost function is 3x squared plus 4, as specified here, which is denoting the total cost of producing x units of a specific good. So what is the marginal cost of production? Well, the marginal cost, again, marginal equals derivative, is the derivative of c with respect to x, and this is simply, you know, the derivative of this function plus the derivative of this function. The derivative of this function is 6x plus the derivative of 4 is just 0. So your marginal cost, which is c prime of x, is going to be equal to 6 times x. So now we'll talk about a few more differentiation rules. There are 3 more rules that you are typically going to be using. The product rule. This tells you that when you have a function f, which is the product of 2 functions, g of x and h of x, the derivative of the product is the derivative of the first function times the second function plus the first function times the derivative of the second function. So let's say we have an example such as the one here, where g of x is x plus 2 and h of x is 3 squared. So if f of x is the product of the 2 functions, x plus 2 times 3 times x squared, then f prime is going to be the derivative of the first. So the derivative of x plus 2 with respect to x is just 1 times the second function plus the first function times the derivative of the second function, which is equal to 6 times x. So that's how we are going to compute it using the product rule. Now, what if a function it can be written as the ratio of 2 functions, gx over hx? Then the quotient rule gives us an idea as of how to compute the derivative of the ratio. And you can see it here. So let me erase the previous one, so then we can do that example over here. So let's erase this thing here, and now let's focus on this rule. So now let's say that f of x is, again using the same example, x plus 2, our g function, divided 3x squared, which is our h function. So what is f prime of x going to be? Is the derivative of g, which is 1, times h of x, which is 3x squared, minus g of x, which is x plus 2, times the derivative of h, which is 6h, divided by h squared, which is 3x squared. Okay? So this is how you would compute the derivative of a function, which is the ratio of 2 functions. Why do we have these rules? Because sometimes it's much easier to compute derivatives this way than actually trying to, simplify the function and compute the whole thing. And sometimes, it's the only thing you can do. Now, the last function that is, let me again delete this so I have a little bit of space to write. The last function that is going to be very important is when you have a sort of a composite function. So imagine that f of x is g of h of x. So in our example, f of x is g of h of x. So it's basically the function g, which is x plus 2, evaluated at h of x. So it's 3x squared plus 2. Okay, this is our g of x, and the other one is, our h of x, and the other one is our g of x. So what is f prime? F prime of x is the derivative of g evaluated at h. So the derivative of g, so what is g prime of x? G prime of x is just 1. So this is just going to be 1 times h prime of x. H prime of x is just 6x. So f prime is going to just be equal to 6x. Notice that if you had actually took the derivative of this function directly, you would have obtained exactly the same result. Now, this last rule is called the chain rule, and it's, let me emphasize it, is going to be very important because many times you have, for example, a utility function, u of c is the natural log of c, and then you have a budget constraint that says that your consumption is wn plus s. So sometimes what you want to figure out is how much does your utility change when you change the number of hours worked, and you can compute, so what is the change in u when you change n? That's going to be the change in u when you change C, which is this part here, times the change in C when you change N, which is this part here. So in other words, it's U prime of C times C prime of N, where C is evaluated at the budget constraint. Okay, so this is going to be used a lot when you are doing maximization and you have more than one variable, say consumption and number of hours worked, and you're trying to find an optimum, a maximum, or a minimum, and you want to simplify your problem to a function of only one variable. So then you are going to replace, say, the budget set into the objective function so that your equation becomes a function of only one variable. And sometimes when trying to maximize this function, you will need to be using this chain rule. So remember it, because people sometimes get confused. Composition of functions and chain rule, they are fancy names, but these are things that you have done in economics. It's typically when you are replacing a budget set or a constraint into an objective function and taking derivative of that. We are going to see more examples when we do optimization. So now let's see an application of this chain rule, because it's going to become handy and it's going to help you fix ideas. So let's say a manufacturer of pencils estimates that T months from now it will sell X million units per week, where X can be summarized as this function of T. Remember, T is how much, X is how much you're going to sell T months from now. So depending on whether T is 1, 2, or 3, you're going to have this quadratic relationship between T and X. Because of economies of scale, the profit P from selling those X units is going to be this many millions of dollars. So this is a function of P that depends on X. So the first question is, what are the marginal profits of this manufacturer? So remember, marginal profits is a derivative. You're being asked about what is the change in P when you change the number of units sold. And this is just 0.001 times 2 times X. Okay, that's going to be your marginal profit. Now, there is a second question. This is a little bit trickier. At which rate will the profit be increasing T months from now? So this is asking you not about the marginal profit, not how much more money you're going to make if you sell more units, but how much will your profit be increasing when T increases marginally, T months from now. So basically what you're being asked here is, what is the change in profits when T grows by 1 unit? And again, we know that we can write P as a function of T using this relationship here. So this is like our G function and this is our H function. And we know that if we plug X here, we are basically using the composition of these two functions. How do we answer this question? Where we can use the chain rule. So the change in P when you change T is the change in P when you change X times the change in X when you change T. So what is the change in X when you change T? We can compute it from the first equation, is 0.05 times 2T plus 2. It's just the derivative of this function. What is the change in P in profits when you change X? That's marginal profits. We computed it already. So it's going to be 0.001 times 2X times the change in X when you change T, which is 0.05 times 2T plus 2. Okay? And again, we know what X is from this equation. So we could plug X here. So it's 0.001 times 2 times 0.05T squared plus 2T plus 5 times 0.05 times 2T plus 2. Okay? And that's the formula for at which rate will the profit be increasing T months from now. Now, the last question is, at what rate will the profit be increasing 5 months from now? So all this question is asking you is, what is the value of dp/dt when t is equal to 5? And if you plug t equal to 5 in the formula we just computed, and I didn't mess up on the calculations, this should be 0.33, and I let you compute it to check. Now, one other differentiation rule that is going to be useful and that is given by the chain rule is a method for calculating the derivative of inverse functions. So what is the derivative of the inverse of f is 1 over the derivative of f evaluated at f minus 1. How can we do this? Well, we can again use the chain rule. So what do we know? We know that by definition the inverse of f is a function such that when you evaluate f at its inverse, you recover back x, and this works for all x in the domain. Now, if we take the derivative of this function and we use the change rule, then what is this thing? Is the derivative of this is the derivative of f evaluated at f minus 1 times the derivative of f minus 1 evaluated at x. We take the derivative on the two sides. What is the derivative of x? Is just 1. And then we divide both sides by f prime f minus 1x, f prime f minus 1x. We simplify and we get back the result. Okay, so the chain rule is giving us a way to compute the derivative of the inverse of a function. The last two differentiation rules, we are not going to prove them, but we are going to be using them a lot, is how to compute the derivative of the exponential function and the natural logarithm. So the derivative of the exponential function is just the exponential function itself. The derivative of the logarithmic function is 1 over x. These two particularly are going to be very useful later on because, as I said before, we like our utility functions to take one of these two forms. So many times you're going to be computing marginal utilities, so that if your utility function is a natural log of x, your marginal utility is going to be 1 over x, and this is something you are going to be using over and over again. Now, are functions typically differentiable at all points in the domain? Well, this is not necessarily going to be the case. So there are functions that are differentiable everywhere, and there are functions that are not differentiable at particular points. When is a function undifferentiable? Remember, the derivative of a function is the slope of the tangent line. So if a function does not have a tangent, say because it has a kink, or because it's discontinuous, or when a function has a vertical tangent, so something that is not well defined, the derivative of a straight line is not well defined, then you are going to say that the function is not going to be differentiable at that point. So in this example, wherever there is a kink or a vertical tangent at a point or a discontinuity at a point, we are going to say that the function is not going to be differentiable at that point. Now, the function may be differentiable at other points in the domain, but it's not going to be differentiable at point A. Now, another thing that we are going to be using a lot is the second derivative. So what is the second derivative at the particular point x0? Well, the second derivative is the derivative of the derivative. And this again is going to be a function itself. How do we denote the second derivative? Well, either by f prime prime of x0 or by this thing here. Okay, if both the derivative exist, the first derivative and the second derivative exist at a particular point, then we are going to say that the function f is twice differentiable at x0. When do we use this thing? As we are going to see in a bit, we use differentiability first and second derivatives to talk about the shape of a function. So so it's important to know whether the first and second derivative exist. Now, if f is twice differentiable at every point in the domain, we say simply that f is twice differentiable without saying at point x, and we, just simply denote it by f prime prime. So let's see an example. If f is 6x cubed plus 2x squared plus 4, the first derivative is 18x squared plus 4x plus the derivative of 4 is just 0. Here, notice we use a lot of the rules that we talked about before. We use the fact that the derivative of the sum is the sum of the derivatives. We use the fact that the derivative of a power rule where the power is n to x to the n minus 1. And we use the fact that if we have a constant times a function, the derivative of that is the constant times the derivative of the function. What is the second derivative? Well, basically what we do is we take the derivative of the first derivative. So it's 2 times 18 times x plus 4. Okay, that's going to be the second derivative of the function f. Notice that, as I said before, this is a derivative itself. If a function is if a function is twice differentiable, so we can take the second derivative and both the first and second derivative are well defined in the domain, and the second derivative is continuous, such as the case in the example, we say that the function is twice continuously differentiable. Why am I giving you these definitions? Because sometimes, again, when you have an economic environment, your professor is going to say, imagine that the production function is twice continuously differentiable. So then what do you need to remember? Well, we are going to have in mind a function of which I can take two derivatives, and the two derivatives are going to be continuous in the whole domain. This is going to be useful in cases where your professor wants to talk an environment without giving you a particular functional form.